Welcome back. Everyone ready to get started again? Okay. Did you want to know anything about the test? Not today. I'll do it tomorrow. What I want to do today is I want to move into the next section. I want to show you how it's connected. However, tomorrow, at the end of class, I'll get you back the exams. Overall, good. You'll be able to see your scores in Canvas if you go into the grade book. Once you do get them back, any question that was missed, I will give you a little breakdown, but you can do test corrections. And what that will involve is stating what your answer was, why it was wrong. So you want to identify what was your misconception, whatever it was, and then what is the correct answer and why do you understand that to be the correct answer now? So it'll be a little bit more involved, but not too much. You can get help because you'll get the right answers from somebody's got the right answer in here. But then that way you get half the points back. So that puts everyone in a good shape. And then remember that for the final exam, as you learn more things, if you get a higher score on the final, it will replace any of your lowest scores. So that was coming on. Let's see. And I do have a couple makeups, so that's the other reason I don't hand it back right away. Oh. That's why. Okay. The other thing, I looked over, a number of you got all the homework done, 100%, all the homework quizzes. Some didn't. You can still work on it to get it up there. It does help the overall grade because homework and the quizzes are worth 30% of the grade. So that will help as well. The other thing it does is it helps you learn the concepts more deeply because you're practicing them multiple times in multiple settings, multiple question types. So, but it would be best if you move forward and get all of that sort of wrapped up this week. So I'll give you the test back tomorrow. You've got about a week to get any corrections done and back into me. And then the main thing is to keep moving forward. Take a look at how you did. If you weren't as successful as you wanted to, think about how did you go about working through things? How could you maybe improve next time? And if you did well, what were the things you did? Let's do those things some more. Just keep doing it and keep learning. Okay. So the best way is to keep moving forward. So we are now into chapter 4. And what we are going to talk about today and in this section is something called probability. And in this time, this is why I thought everything was set up. This one does have the textbook in there. It was already in there. So I encourage you to take a look at the textbook. Much of it will be covered during lectures and in the slideshows and stuff, but it's a good thing to at least scan over empirical probability. What is it? We'll talk about these things, but you get some definitions, you get some examples, and a number of these you'll see in the slides as well, but it's always good to go back and take a look at the textbook. Okay. Okay. So if I say the word probability, what does that make you think of? A chance of something happening, or chance of something not happening too, right? Because it's either something happens or it doesn't. So exactly, it has to do with the chance of something happening, and usually randomness is involved. Okay, somewhat involved. It's a chance of rain today. Well, I see no clouds, and we look on the weather, and sometimes they say 0%, sometimes 10%, sometimes 50%, those kind of things. Okay, what does it mean for something to be random? Unexpected? Not. It could involve equal chances. Here's a definition from the what do they call those things? Dictionary. So it's without a definite plan or purpose or pattern, and mostly we're looking at there's a pattern. So if you open up a brand new deck of cards, would you say that those, for those who have experience with cards, are those cards random? No, they're, in fact, they put them in a particular order. They're in a particular suits. They're 2, 3, 4, 5. So there's a particular pattern to them. So we don't call those random. So what's the first thing you're going to do if you play a card game? You randomize them by shuffling, right? You take out the pattern. So that's the idea, is if there's patterns, if there's like a purpose or something, and I am choosing something on purpose, and my biases are getting involved and such, that's not random. What we're going to talk about are processes that are completely random. I've got a die. Like at the casinos, they've got games where you roll the die. How do people cheat at that? They weight it. They load the dice. They call it loaded dice. So it's more likely, and maybe it won't always do it, but it's more likely to land on particular numbers. That's not random. Okay, you use those when you want to win, right? You throw that number, and but a regular set of dice, we could roll them multiple times, and we'd say, yeah, it's random, right? Whatever number is going to come up is somewhat random. So that's the idea that we're working with when we talk about probability. And what I want to do is I want to tie it back to what we've already done. This comes out of chapter 2. We were looking at constructing a frequency table, right? And then we also used histograms from. So a lot of stuff that we're going to cover goes right back to what we were doing to this. So what was the first step in coming up with a frequency table? Well, we made our classes. We're not going to go into that, but we would divide them into groups. And that was on the test, so hopefully you understood how to do that. And then in those classes, what does this tally mean? What are we doing with this tally? Excellent. Excellent. So there's the aspect of counting. So this is the math we're doing. We're counting. How many of you know how to count? We've been counting since we were little kids, right? And even before we knew the names for those numbers, we could count things out. We had some candy. We could divide it between our brothers and sisters, right? Just one for you, one for me, one. So we've been able to count for a long time. That's the main thing we're going to talk about today. So we count those. And then these tallies tell us how frequently there's a piece of data, in this case, that is between 155 and 190, right? So those frequencies are how many times that occurs. So looking at this, if you randomly were to select a number or a class, which class do you see from that table would be the most likely to be selected? Oops, let's go back. Between 299 and 334, because why? There's more of them, right? There's more, so we would say that's the most chance. Which one would have the least chance of being selected? Excellent. So you're already experts at probability. This is how we do probability. Now, all we're going to do in this first section is change these frequencies from amounts to a relative frequency, which is a percentage, right? So when we were doing these frequency charts, how did we calculate the relative frequency? We divided. So we took the frequency and we divided it by the total. We may not have called it a probability, but that's exactly what we were calculating at this point. What percentage of the data is in this? So 3 divided by 30, we would have came up with 0.10, 3 divided by 30. And we could also turn it into a percentage, so we could list it as 10%. So there's 3 ways to write probabilities. One is as a fraction. Actually, let's do it as a reduced fraction. So 3 divided by 30 reduces down to 1/10. We could use it as 0.10 or 10%. My preference is 10% because I like working with percentages. I don't really like decimals that much. I certainly don't like fractions. So I could deal with them if I have to, but I like percentages. But these are 3 different ways to express the probability that 155 to 190 has a 1 in 10 chance. It has a 10.1, a tenth of a chance, or a 10% chance. Those all mean the same thing. Okay, so if we were to randomly select one of these classes, that's what it would be. Now, just because there's 1, 2, 3, 4, 5, 6, 7, doesn't mean they're all equally likely, does it? It's not 1 in 7 chance because some have more marbles in the bag, as it were. Okay, so we go through and as we were doing this, 2 out of 30, 5 out of 30, 6 out of 30, 7 out of 30, and so forth. We may not have thought, we didn't talk about this as being a probability, but if we introduce the fact that we're going to now randomly select a class, these are now probabilities. What is more likely to be selected? And as we saw, the one with 7, what's 7 divided by 30? Anybody? Anyone get it faster than me? 7 divided, oops. I'm in the wrong. 7 divided by 30, 0.23333, repeating forever. So we'll just call it 0.23 or 23% chance. And if you calculate all these others, they're smaller than 23% chance. Okay, so that's why it's the most likely. Doesn't mean we're going to get that, but in the 2 out of 30, that's 1/15th. Just 0.066, so we could round that to 0.07, so about a 7% chance, rounded. And yes, that has the least probability. When we total the relative frequencies, what do we always get? 1. Or if we do the percentages, we get 100%. Okay, so we'll see these 2 numbers coming up a lot in probabilities. 1 represents everything, right? Everything that could potentially happen, 100%. You can't go over 100% in probabilities. What would you think would be the smallest probability of something happening? Could you have a negative probability? 0. It just doesn't happen, right? So it either happens or it doesn't. And if there's something like, can you draw a green card out of a deck of cards? No, there are only black cards and red cards. So green card would be a probability of 0. It's impossible. There is none. Okay, so those that we could have 0, but we can't have a negative probability. So probabilities go from 0 to 1, 0% to 100%. Okay, and all we have to do is a simple process of counting, but it's not always so simple. So we're going to introduce some ways of counting larger quantities quickly. But the whole thing of probability is we count the total, and we divide that into, I'm just going to call it the good things, or whatever we're counting, whatever we're wanting to happen or not happen. So it's just the frequency divided by the total. Maybe I'll just put frequency. And we'll see this again. That's all probability is. Just a simple calculation, a simple division. We can use our calculators, turn it to a percentage by moving the decimal over 2 places, right? Or multiplying by 100. You've all been able to do that. So we can remember we could also make, this was the same data, we could make a histogram, but now when we look at it as relative frequencies, these numbers here can tell us the probability of something happening. So the probability of getting a number between two, or in this class, would be 20%, because 20% of the data is in that class, right? So these histograms are now, we're going to be using them as probability graphs, okay? We sort of started doing that at the end when we talked about that empirical rule. Remember we said a bell shape, there's 68% in the middle. That's exactly what we were doing. We were just using relative frequencies, okay? So hopefully this all connects with, to let you know that we're not just randomly jumping into something completely different or something new. It's really older stuff, but we're now going to apply it in these ways, okay? So here's a sort of the start of what we're usually, they start talking about probability. The number that goes with it is between 0 to 100. If it's 100% chance of rain, what does that mean? It's going to happen, and probably it is raining right now. If it's 100%, really, it is going to happen. 0% chance of rain, no chance. Now, sometimes they're wrong, right? But again, if a 0% means it's impossible to happen. So be careful about it. Most things are somewhere in between. What's the possibility of winning? This Powerball just got up to $1.8 billion. Yeah, 1.8 billion. 2 people got winning tickets. But what was the probability of any one ticket winning? It wasn't 0, because then that means nobody could win. It was a very small amount, like 1 in 290 million or something. I can't. It's a huge number. Yeah, so very small chance for any individual ticket. But then when you look at it, somebody won. So if enough tickets are purchased, there's actually a probability that you're going to get a winner. Okay, so even small probabilities end up happening. And if you were, all you had to do is buy 1 ticket. If your numbers matched, even though the probability was small, you now got like $500 million. I was hoping for. I bought a ticket, but I won $4, but I matched one of the, the Powerball, but no. And there's even games. There's people that have been caught because there's some lottery systems where if the jackpot gets high enough, if you went and bought every single ticket, you'd have 100% chance. And there's some people that have been, and they try to say that's a scamming, but it's not. It's just the way the rules are. There's people who found those things, and they had enough money to buy every single ticket, and maybe it's like $6 million to buy the tickets, but they ended up winning after taxes more than that. So, and then they made a whole system where they had their family just buying tickets. That's the hard part. You have to buy 100% to get a 100% chance. Kind of cool though, right? I wish I would have thought of that. But and then as soon as that starts happening, they change the games to make them harder. And we're going to see how we can do that relatively easily, because we're going to, in our counting, we're going to learn to count large numbers. Okay, but just remember, probabilities are just a percentage, somewhere between 0 to 100%. 100% means it's going to happen. 0%, not going to happen. Anything in between. Okay. What we do is we do things called probability experiments, and that means we roll the die a lot of time, or we flip a bunch of coins to test it out, right? So we go through a trial and we count, and that's how probability was developed. The theory that we use today has been developed. People roll dice a lot of times, and they see, if you do it enough times, on average, you get the 1/6 of the time, the 2/6, 1/6 of the time. So we'll see that the counting does work. Okay. Some vocabulary we're going to use. An outcome is what could happen. So if we're talking about the weather, rain or not rain. So there's 2 outcomes possible. if we're just talking about rain. Sunny, not sometimes cloudy, partially cloudy. But those are all outcomes that we would do. Okay, so the outcomes are the result of a single trial. What could happen? If I'm rolling die, my outcome is a 1, 2, 3, 4, 5, or 6. Is a 7 possible with a regular die? No. It only goes up to 6. Okay, that would be an impossibility. Something we call the sample space are all the possibilities of things that could happen. So if I'm talking die, it's a 1, 2, 3, 4, 5, 6. I could get any one of those numbers. They could all appear, right? Set of all possible outcomes of a probability experiment. So we'll talk about a sample space. Those are all the things that could happen. What does the probability of all the sample space always have to equal? I hear it? 100% or 1. Yeah, so it depends on whether you're talking decimals or percentages. Exactly. If it isn't equal to 100%, then we've left something out. If it's more than 100%, we've counted something twice or 3 times, okay? So a sample space is always 100% probability. And then an event is a single thing that could happen. You know, rolling a 2 is both, it could be considered an outcome if it happens, but it's also called an event before it happens. So we look at all the possible events. So in this way, the probability, calculating a probability is simply taking the number of events, the number of frequencies, the frequency of an event divided by the sample space. How many are in? So the number in the event divided by the number in the sample space. Throw it in there. So again, counting is going to come into play, but we're going to do things like how many 5-digit PIN numbers are possible to make. And we're going to see that we can actually get that number relatively without too much trouble, as long as we know how to multiply. Now, we want to have calculators because the numbers will get very big, but that's all we're doing is we're counting how many frequencies are in that particular event and divide it by the sample space. When we're talking rain, what the weather people basically do is they say these are the conditions today, and then they count back on days like this, how many times did it rain out of how many days, and that's how they can calculate a simple probability. Well, on 10% of the days like today, it rained, so now there's a 10% chance. That's all they're doing is counting most of the times. Sometimes they're guessing, right? We'll talk about that. That's also another type of probability. It's called, well, I forget what it's called, but we've got a slide that talks about it. Okay, so here we get into the counting part. We're going to use something called the fundamental counting principle. Simply put, if you take 2 numbers and multiply them, you'll be able to count how many there are. So we're going to see where that applies. So we have more than 2 groups. So the number of possible outfits, if you have 2 pairs of jeans, 3 t-shirts, 3 different t-shirts, and 2 pairs of sneakers. So how could we do this? We want to see all the different possibilities. And you could kind of go through the process. We'll do a little chart here. So you get dressed in the morning, you got either your blue jeans or your black jeans. You got 3 different t-shirts you could wear. So notice if you choose the blue, you could do the, I don't know, beige, yellow, or blue t-shirt. And then for each of those, you could choose either the black shoes or the red shoes, right? And so what we see with 2 pairs of jeans, 3 t-shirts, and 2 pairs, the total number of outcomes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we could count them, but could you see that if there was a larger numbers, that doing it with a tree diagram, while it would give us, it would be kind of messy and hard. So the easy way to do this is think of this as we branch off to 2 pairs of jeans. You take 2 times 3, you get 1, 2, 3, 4, 5, 6. That seems to work. And then if you multiply that number times 2, because there's 2 more pairs of sneakers, we do get 12. Okay, so that's all it says is when you've got different groups of things, you just need to multiply them. That will tell you the total. And remember, this is what we're going to use for our calculations of probabilities. We're going to divide by this number. So what's the probability of getting a particular, what's the probability of wearing an outfit with yellow shirts? We could just simply say, well, at the end, there's 4 different outfits that have yellow shirts, divided by 12 total outfits. That's a 1/3. So about 33.33%. 1/3 is 0.33, repeating, or 33%. Okay, that's all we're doing. Okay, but again, there's going to be a few other things we look at for counting that we do. Okay, and a couple other examples. Here's identifying the sample space for blood types. So there's a O, A, B, and AB. How many of you know what your blood type is? A few of you? If you're donated blood, they'll tell you. I keep forgetting. I think I'm an A, but I can't remember if I'm an A negative or an A positive. I know it's the opposite of my wife's. Notice if you're positive, you can't give blood to a negative, and if you're negative, you can't give it to a positive. You kill the people, so don't do that. But also, there's certain types that can receive blood from others, so that's the whole thing between typing. So these are the main types. Each has a plus or minus, and so then we've got a sample space for blood types. Okay, so this is the whole part of counting, is you've got to make sure you've counted everything. And again, sometimes it takes some research. Somebody had to go, and find out there isn't another type of blood, or I don't know, maybe there is. Nobody's found it yet, but that's how we go. And so we get what we call the sample space, is all the possibilities of types of blood. Again, some are more rare than others, some are more common, but we now have the sample space. Okay, so we'll use this quite often. We're going to next look at an experiment. One thing is they're going to flip a coin. So the first thing that happens is you get either a heads or a tails. And then the next thing they're going to do is they're going to roll a die. So then you get either a 1 through 6. But if you got the heads, the way they're going to put the outcomes is you got a head and then a 1, a head and a 2, and so forth. Or you got a tail and a 1 and a tail and a 2. So these are all the outcomes, and how many potential outcomes are there? 6 and 6 is 12, right? So 12 possible outcomes. So we call a simple event something that has only a single outcome. Okay, so if I toss a heads and roll a 3, how many times does that happen? Just once. There's one outcome that would make that happen. So that's a simple event. What's an example of a non-simple event? Well, if I toss a heads and then roll an even number, so here's a heads, an even number would be, I'd roll a 2, a 4, or a 6. That is not a simple outcome. It's not a simple event, right? Because there's more than one thing that happens. And so we're going to break these apart. We'll see that today we'll deal with simple events. Tomorrow we start dealing with non-simple events where there's more than one outcome. And again, it's all just about counting. We could get these probabilities. Well, there's only 1 out of 12 chances of this happening. So that's 1/12. Get the percentage. How many? There's 3 out of 12, which is 1/4 or 25%. So calculating probabilities is very the same. Again, it's just simple division. Simple. Counting and dividing. Okay. And again, this is just what we were talking about. Fundamental counting principle is simply if you have an event that can occur m ways and then a second event, so that we're grouping things, think of things one thing and the next, you just need to multiply them. So that's all the fundamental counting principle. My teacher called it the multiplication principle. You're just going to multiply. Okay. And again, if they're big numbers, we can use our calculators. Small numbers, maybe we know it, but we still can use our calculators. Okay, so just think mostly what we're doing here is multiplying. There's a few times when we're going to add, but that's mostly what we're doing is multiplying. Okay. So if you're going to purchase a new car, you've got some choices. You've got, say, maybe 3 manufacturers, 2 different sizes of cars, and 4 different colors. So how many different cars could be selected from this menu? Well, there's 3 manufacturers, 2 sizes, and 4 different colors. Looks like 8 times 3. There's actually 24 different cars that could come out of the selection. And again, you could do a tree diagram to do it, but it's going to get a little messy, right? I think they do it. They say, yeah, it's going to be 24 ways. Here it is. You know, again, if I were doing it, it would be very messy because my handwriting's not all that good. But okay, so you could see it. Okay, yeah. So just sort of start to visualize that sort of step by step that we're multiplying, and then that gives you a feel for things. So visualizing. Now we're going to calculate some, and these are kind of cool. So we've got access code for a car security system consists of 4 digits. Now the thing you have to remember, how many numbers do we have for each digits? How many possibilities? Some people will say 9 because there's 1 through 9, but what about 0? We could use it. So there's actually 10 digits. There's 10 different symbols that could go in for each digit. So 10. So the way we think about, well, let's, this may seem like a simple access or problem, but we're going to add 3 different things. So one, we're putting a rule: each digit can be used only once and not repeated. Each digit can be repeated, and each digit can be repeated, but the first digit cannot be 0 or 1. Sometimes there's those kind of rules, like when you're calling on a phone, area code cannot be start with a 0 because that puts you to the operator. Also can't start with 1 because that's supposed to tell you you're doing long distance or out of your area. So those kind of things happen. So here's the way we go about counting. We've got 4 digits. So let's think about it. With this first one, each digit can be used only once and not repeated. So how many different digits could we put in the first place? 10. We've got 0 through 9. Okay. So we use one of those. Can we use it again? No, because we can. So now for the second digit, how many symbols do we have left? We only have 9 because we've used one. Then for the third digit, 8 because we're using them up. So you're going to see this. This is something called a factorial, actually, if you go all the way down. But we'll be doing this quite a bit. And it's also a permutation when you can't repeat. So we would multiply these all together. I think it's 5,040. 10 times 9 times 8 times 7, 5,040. And again, I've just done this so many times, I remember this one. Okay, there's 5,040 different codes that could be happened. Now, how could we get more? Well, this next one says you can repeat the digits. You think we'll get more codes? Of course, it seems like we should. So we've got 10 for the first. We could repeat it, so we got 10 for the second. We can repeat it, so we've got 10 for the third and 10 for the fourth. This one's, you know, when you're multiplying with tens, you just count the number of zeros. So it's a 0 with actually 4 digits, 4 zeros behind it. So 10,000. So twice as many by being able to repeat. Okay. And then the last one, and you'll see this, they'll have some in the homework that are like this. If we can't use a 0, 1 for the first one, so for the first digit, how many different symbols could we use? 8, right? Each digit can be repeated, but the first digit. So we've only got 8 here. After we get past the first digit, how many digits do we have for the second? 10, because we can now repeat them and we can use 0 and 1. So part of it is understanding the rules. They're not always real clear, but yeah, then it's 10, 10, and 10. And so, oops, not 18, 10. And so that's going to give us 8,000 different codes. Okay, so you could see the effect of changing the rules on things. Which one do you think is going to be the most secure? One with 10,000 codes, because if someone's just randomly guessing, they got 10,000 codes to guess through instead of 5,000 codes to guess through. Okay. Although they say you shouldn't repeat shouldn't do 1111 as your code, but that is an option. Okay, so far so good. Again, counting, just this multiplication principle. And again, this is what we started off with. It's the number of outcomes in an event, right? The frequency of something happening divided by the total stuff that's could possibly happen. So we find the total divided into the number of events, and that's our probability. That's all there is. Okay. Now we're going to see if we can make it a little bit more complicated when there's more things that could happen and stuff. So it's and the hard part of probabilities, you got to really read those questions carefully because a change in one word changes what it's really asking about. Okay, so we'll get to those, but it's all the math part is not the hard part. Hard part is understanding the English. That's where I always had the problem. I had to go to the professor and he says, "No, you got the right idea, but because of this word saying is or saying and or saying or, it all changes it." So those little words make a big difference. Okay. Roll a 6-sided die, find the probability of each event. So event A is rolling a 3. What's the probability of rolling a 3? Well, how many 3s are on the die? How many total numbers are on the die? 6, 1, 6. Rolling a 7. How many 7s are on the die? 0 out of 6. So there's 0% chance. Rolling a number less than 5. Less than 5. How many numbers are less than 5? 1, 2, 3, 4. So counting with the fingers help. 5 is not included because 5 is not less than 5. It's equal to 5. So that would be 4 out of 6, or 2/3. About 66%. Okay. So you see, that's all we're doing for this first part. And what the important part is, this is sort of a little sidestep. I thought this was a statistics class. Now it feels like a gambling class or something. But that's what gambling's all about, chance, right? But what we're going to see is this is the basis that statistics is built on. Okay, so we spent the time kind of learning the details about statistics and everything. Now we've got to learn some things about probability so we can tie the two together. And we'll do that in chapter 5 is when we move on. Okay, so sample space, yeah, there's 6 things that could happen, and then we count those. Now, empirical probabilities, we talked about the empirical rule before. It simply means observed. So it's what we see happening. So this is like in, how many of you are into some sort of a sport? Right? And whether actively doing it or watching it, my brother's like the walking sports encyclopedia. He knows statistics, right? How many times at bat. This is the types of things, the probabilities. So we count how many times the person came to bat, how many times they got a hit, and that's their batting average. Pitcher has a earned run average. How many times do they pitch? How many hits do they get? Those kind of things. It's all empirical probabilities. Free throws. How many free throws did you try? How many did you make? I'm usually at about 0%, but that's why they don't let me play that game anymore. But my friend's much better than me. So sports is all built on empirical probabilities. And again, you could have a good day and a bad day. So just because you have a 50% free throw probability doesn't mean you're going to make half of them all the time. Sometimes you have a bad day, sometimes you have a good day. But that's what we use it for. Okay. So here's a long thing, but a lot of times they'll give us what we need. So companies conducting a survey, randomly selected U.S. adults. So this is the random part of it. So far, they have 1,502 adults who have been surveyed. Our pie chart's down here. What is the probability that the next adult survey read only print books? Let's see. Read only print books. So there was, on the survey, there was 560 out of 1,502. So how could we calculate that probability? Just divide it. Exactly. It's already been counted for us. And just divide it, and we'll get a probability. Is that about 30%? Pretty close. 560 divided by 1,502. 37? Okay. 37%. Okay. So again, we use statistics to calculate these things. But again, it's about if we were to randomly select somebody. If I go out and I'm looking at people, maybe my bias, I think that person's one who reads it. It's no longer random. Okay. If it's random, that's where probability happens. And again, they went through and added them all up, but we were told 1,502. Yeah, 37%, 37.3. Okay, so we can, and again, just watch for when you're doing the homework, you'll be able to do about the first 10 again once we're done with today, which we're almost done there. But just watch whether it wants it as a decimal or as a percentage, because you might have the right numerical answer, but if you give it in the wrong form, sometimes they'll have a percent at the back. They want it as a percent. Sometimes they want it as a decimal. Sometimes they want it as a fraction, a reduced fraction. Okay. I'm going to skip over, well, we don't have to skip too far, but remember, this is sort of what we started with. This one, we're told that there's a total of 3,000 users, and that's from the frequency table. That's what they tell us down here. And again, what's the probability of getting someone 25 to 34? Well, from the sample, there was 765. So again, it's just a simple division. 765 divided by 3,000. That's our probability. We can write it as a decimal or percentage, or we could do it as a fraction. It's all the same. Okay. So far, so good. And this is the math part of this is the easy part. Again, it's the English part. As we get to learn more different things that could happen, we'll look at conditional probabilities where we know something. So knowing what to count, that's going to be the hard part, but not too hard. Okay. So the law of large numbers simply states that if you flip a coin 5 times in a row, would it be possible to get 5 heads? Have you ever had that happen? I don't know. I've never tried it 5 times, but we could see that, you know, it wouldn't be too. Now, if you flipped it 100 times in a row, would it be likely that you got all heads? By that time, you're probably saying maybe this coin is weighted or something. Maybe it's a, you know. So yeah. So large numbers just means that if we do it a few times, we could get, anything could happen. We get all heads, we get all tails, get a mix. But the more times we do it, we're going to get closer to half of them being heads and half of them being tails, as long as it's a fair coin. Okay. Same thing with rolling dice. So that's all it is that you have to do an event a lot of times. Okay. So like, that's what people make the mistake when they go to the casino. In the long run, who's going to win at a casino? Casino, because the probabilities are in their favor. That doesn't mean you could go in and you could win big jackpot. My friend always tells me, when you do that, you go back to your car and you put that money away. If you want to play a little bit, you go, but you know, because otherwise what happens is people win the jackpot and what do they think? That's my lucky day, so I'm really going to win a lot. No, they lose it all again. So it happens, but the probabilities are in favor of the casino. Go and have some fun, I guess, but when you win, notice that that's a rare event. You better that's the time to leave. Unfortunately, most people don't. They give all the money back to the casino, and then that's how it works. Yeah, and then they cry all the way home. Or yeah. Okay, this is the other one I was talking about, subjective probabilities. I think we'll stop here today. But subjective probabilities is sometimes you say you're waiting for your friend, and you say they're going to be late, or maybe they're not going to show up. And that depends upon past, right? You're kind of going to back to, okay, Jake, maybe he's flaky. He maybe forgot about it because he does that a lot. Maybe he's taking a nap or something. So my friend Jake, my other friend, Nick, he's always going to show up. So I figured something got stuck in traffic. But that's all subjective. That's just our feeling from the past, okay? So that's part of probability. And sometimes based on things. So we've got 3 types of probability. One is what they call the classical, or we just count, right? Empirical, we watch what happens. That's usually think about sports. And then the last one is subjective, is we just think it's going to happen. Okay? And we'll pick up tomorrow, and I'll get you back your tests. You can start working. I'll show you how to do test corrections, and we'll keep moving forward.